Welcome to part 4, estimating logistic function parameters. In this video, we're going to smooth the data first. We're going to estimate parameter bounds for our three logistic function parameters, L, X naught, and K. And finally, we're going to use the least squares function from SciPy to estimate what those parameters are and to complete the building of our model. So here we have cases from Italy, and we're going to smooth them up to April 1st. So this will be our training data, the smooth data in orange. The actual data is in blue. So what we want to do is we want to build our logistic function model. That means we need to find the values of L, X naught, and K that will match this curve the best and really into the future. So we're going to model future data. We're just giving it data up to April 1st at this point. We're going to use this input to build our model. So we need to find bounds for L, X naught, and K. And what we're going to do, it's very difficult to figure out what are the right bounds. So we're just going to give very wide bounds for both L and X naught. And for K, we are also going to give wide bounds, but we need to have some idea of where K is located. It's a little easier to see L and X naught. So for instance, L is the maximum value of where the asymptote is for the logistic function. So here we have a value of 100,000, so it's going to be a minimum of 100,000. Now, the maximum we could say is maybe 10 times this. We don't know how far it will go for this particular coronavirus case wave, but we can give some estimate, and we'll just give a very wide one. Same thing for X naught is the midpoint of where half of the cases for this current wave are going to happen. Is it after 30 days? Is it after 50 days? Is it 100 days? So we can give a wide range there. For K, we might not have any clue of what value it could be. So what we'll do is we'll complete this exercise, which will plot different values of K for fixed values of L and X naught, just to get a sense of its range. So that's what this exercise is all about. So we're going to write a function that accepts the data to be modeled as a series. That's S, a list of potential Ks. So we're just going to see how the curve performs based on different values of Ks that we give here. A single value for L and a single value for X naught. So we're going to hold L and X naught constant and see how the value of K, how the curve looks with K. So we're going to plot the logistic curve starting on the same date as the past data and continuing for twice the amount of X naught. So we're going to see how it looks into the future. So the way this is going to work is we're getting this value, or the series S. So we're going to make another series for the guesses, for the potential curves with K. And the way to do this is we need to get the date range aligned. So we're going to get that first index value, which is a date, that's the starting date. And we're going to create a new index using the date range function in pandas. So we're going to use that starting date. So one way to use this function is to give it the start, give it the number of periods. So we want it, actually we want to say 2 times X naught. So if we say X naught is 30, it's going to go for 30 or 60 days. And so now we're going to build our model. So we're going to say the length of the index over here. Y will just simply be the logistic function of given this X and one of these K's. So we actually need to write a loop here. So X will remain the same. We'll say for K in K's. And we're going to give it, if we look at our documentation, L, whatever L is, X naught, and then the current value of K. And now we need just the current, I guess we can call it just guess again. We're going to create a series here of Y, and the index will be this index right here. And then we will just plot each one. We need to make sure we give it the label. So we're going to say it's this particular K. And we will call the legend function in order to, or method in order to display the legend like that. What we need to do is also graph just the smooth data or the input data at first. So we're going to get that, and then we're going to plot all of these values of k as such. Okay, so this should work. So we're going to call plot k's, and we're going to give it the Italy data. And now here's where we give it a list of k's. So this is where we just want to, you may have no idea. So we'll just give it a bunch of k's. L, so we can play around with this as well by calling it multiple times, but we can start with, let's just say it was around 100,000. So if we look over here, what is a good guess for L? Maybe it's at the halfway point, so at 100,000, maybe we can go with 200,000, and then x naught is the halfway to the number of days since the beginning, so if you count the beginning way over here, maybe it's 40 or 50 days, so let's do that. Okay, so here's our first attempt at doing this. So the blue is actually, so the blue is the smoothed, and actually I should use the smooth data. That's what I not do, so call it y smooth. So there we go, and maybe to differentiate it, we can say for the smooth data, we could say the line width is a little bit thicker so we can see that a little bit. So this is the actual data. And so given a L of 200,000, that's a limit, and a midpoint of 50, you can see different values of k. So when k is, let's go ahead and look at the ones that are really probably will not work. So a k value of 1 is very, very steep here. And we can see that the actual data, this blue, is certainly not as steep. So it looks like it'll certainly be less than 1. Now, if you look at, okay, then 0.5 is still quite steep, and the line looks to be, k looks to be less than that. Then we get a little bit closer. It looks like, okay, so a value of 0.1 looks like has similar steepness. A value of 0.01 is just too flat. So in this case, it certainly seems like the maximum k would be 0.5, and it probably would not be less than 0.01. So that's how we can sort of triangulate the value of k and get a range. That's the whole point of this exercise, is what is the lower and upper bound for k? Now, if we change this a little bit, let's just say, we can still go around like this. Say we want the maximum value to be 300,000, and maybe x is a little bit less. Let's see, what does it look like here? Well, certainly looks like x naught is a little bit low, but regardless, it's still okay to see what happens here. Now, what we're really interested in is this, is really the rate of change, and it looks like, again, 1 and 0.5 are too steep, and 0.1 looks pretty similar to that growth rate over here. So again, we're just trying to triangulate what k is. If we make this a little bit larger, the x naught, so we're still back to a k of maybe 0.1 or even maybe a little bit less. So we'll let the least squares function figure that out for us, but it's still a decent exercise to see where this k would be given different values of L and x naught. So that's what we'll do. We'll probably say anywhere between 0.01 and 0.5. So let's go down here to choose the bounds, and that's what I've done. So the lower bounds, this is for L, it's in order L, x naught, and k. We'll say the lower bound is just for L is going to be the current last value. So it'll certainly go higher than that, but we'll just bound it by that. For x naught, we'll say, okay, 20 days is the lower bound. And 0.01 for k. So we are going to use that 0.01 for k. For the upper bound, we have 1 million, so that's 10 times the amount of where it is right now at around 100,000. 150 days as the maximum for x naught, and then 0.5 for the upper bound of k. So it looks like it's almost certainly less than 0.5 and almost certainly greater than 0.01. So we're going to use those as our bounds, and we'll just use the lower bound as the initial starting value. So you could pick this manually, but here we'll just allow it to be the lower bound. And then we're going to use our nice predict all function that we came up in the last chapter, and it will do all of the work for us and automate that process. We're going to give it the series to predict. I'm going to begin from the very beginning. I'm going to go up to April 1st. I'm going to do 50 new predictions. And then this is the key. We're going to model with the logistic function and we're going to give it the bounds we just created. So let's make sure I enter that in and give it a title for the plot. Okay, so here is what it came up with. So here's our model right here in orange. And we don't see, it looks like it just fell off very quickly, but that's what you can see, that if you cover up the blue line above the orange line, you could say that it looked like it could have taken this path. It just happened not to. Here we're going to give it a little bit more data to train on. Actually, before that, let's look at the parameters. Sorry, so let's go ahead and run this without it. So here are the parameters. So it came up with the L, X naught, and K. So the maximum here is 136,000. The X naught, so the time until the midpoint, about 38 days. And the value of K was found that to be 0.16. So right in that range that we're thinking about above, we're looking at it, it looked like a lot of them were 0.1. So that looks good. And let's also just look at these. So now we're going to give it data up to May 1st. And again, it looks like it just trails off very quickly. And found different parameters here. X, significantly higher for the maximum, over 200,000. The X naught increased, and the K was again around 0.1. Okay, so in the next chapter, or the next video, we're going to talk about how to improve on this model. But so far, it doesn't look like it looks like it's trailing off much too quickly. We'll find a solution to that to help it match quite a bit better. So that's how we estimate parameters for the logistic function. We have to find those bounds, and once we have those bounds, then we can use our normal least squares and our predict all function to come up with the estimates.